Hello everyone, welcome back to the next lecture of differential equation. In last session, we saw how to solve exact differential equation. Now, in this session, we will see how to solve the differential equation which is non-exact. We have seen that the differential equation is called exact if it is satisfying dou m upon dou y is equal to dou n upon dou x equality, where m and n are the functions of x and y, and the differential equation is of the type m dx plus n dy is equal to 0. If this equality doesn't hold, then the said differential equation is called non-exact differential equation. So today we will see how to solve such differential equations. So sometimes differential equations are non-exact, but we can make it exact if we multiply the differential equation with suitable factor known as integrating factor. Okay. Now there are many methods to find out integrating factor. First two you can see on the screen. So if dou m upon dou y minus dou n upon dou x, if we divide this by n, then resultant function, if you are getting the function of x only where y is completely removed, then the integrating factor can be obtained using e to the power integral of that f of x dx. But if we divide it by m and the corresponding result is a function of y, then integrating factor is nothing but e to the power integral of such f of y dy. So these are the two methods in today's lecture we will see. It is known that if we multiply given non-exact differential equation by this integrating factor, then resultant differential equation becomes exact. Now we will see few examples over. So type 1, if dou m upon dou y minus dou n upon dou x, if we divide it by n, then result is the function of x. Y is eliminated here. Then integrating factor is e to the power integral f of x dx. Have first example. So here we can see given differential equation is of the type m dx plus n dy. So before starting, we write m and n in separated form. Then we check whether given differential equation is exact or not. So to check whether the given differential equation is exact, we find derivative of m with respect to y partially. So it is nothing but a 2y, and partial derivative of n with respect to x, which is minus 2y. So since they are not equal, we can see dou m upon dou x is not equal to dou n upon dou x. One more thing here, we are matching this differential equation with mdx plus n dy. So if minus sign is there, that minus sign is a part of n. That's why n contains minus of 2xy. If you forget to take this minus sign, then you may have 2y is equal to 2y, that is the exactness. So that could be the error. So this shows that it is non-exact. Now today we will see how to solve such examples. So the procedure is, first we find out integrating factor. You can see dou m upon dou y minus dou y upon dou x is a 2y minus minus 2y, that is 4y. So if that 4y is divided by m, then we cannot eliminate either x or y. But if we divide it by n, then y can be cancelled and x can be taken as a function of x. So with this observation, we go for dou m upon dou y minus dou n upon dou x if we divide it by n. So this is 2y minus minus 2y upon n is minus 2xy. So this is 4y upon minus 2xy. So this is something minus 2 by x, a pure function of x. 2y is cancelled throughout. So pure function of x we got here. And that's what we wanted. We wanted function of x only. If so, then integrating factor is nothing but e to the power integral of this f of x dx. So we get e to the power integral minus 2 by x dx. So this is e to the power minus 2 constant. Integral of 1 upon x is log x. And that's why same thing can be written as e to the power log of x raised to minus 2, and that is only x raised to minus 2 or 1 upon x square. So this is our integrating factor. So theory says that if we multiply given non-exact differential equation by this integrating factor, then resultant differential equation is exact. So therefore we call this equation as 1.
So multiply, we get x square plus y square plus 1 upon x square dx plus n dy, that is minus 2xy upon x square dy is equal to 0. And this is exact.
No need to check here, but you can always verify. Taking this new m and new n and differentiate this with respect to y and x, see their equality, it will be exact. Okay, now we will see how to solve this differential equation. In last session we have seen how to solve exact differential equation. Therefore the separated form of this is 1 plus y square by x square plus 1 by x square dx plus minus 2y upon x dy is equal to 0. Integrate with respect to x. So integration of m, that is 1 plus y square by x square plus 1 upon x square with respect to x. This gives us integral of 1 is x plus y square. Integral of 1 upon x square is minus 1 upon x, because derivative of minus 1 by x is 1 upon x square. Similarly, integral of 1 by x square is minus 1 by x plus, say, c1. And we know that second part is nothing but the terms in n free from x. This is with respect to y. So in a new differential equation, this is our capital N. So it contains function of x. That's why there is no term which is free from x. That's why its integral is some constant, say c2. Therefore solution is addition of these two, that is x plus y square into minus 1 by x minus 1 by x, and c1 c2 all collected as they are arbitrary constant on RHS. So this is our final answer for non-exact differential equation. So we saw given differential equation was non-exact, but it can be made exact if we multiply by integrating factor. Now how to solve integrating factor? There are many methods. We are looking the first method, that is if dou m upon dou y minus dou n upon dou x, if we divide it by n and if result is a function of x, we find out integrating factor as e to the power integral f of x. But if we divide it by m and if result is function of y, then also integrating factor is e to the power integral of f of y dy. That is our second type to get integrating factor. We have one more example of this type. Now in this example, if we match this with the format mdx plus ndy, we get m as coefficient of dx, that is 2y. So m is 2y and n is the coefficient of dy, that is 2x log x minus xy. Let's see whether differential equation is exact. For that we need two derivatives, m with respect to y, which is 2, and n with respect to x, that is 2 into x log x u into v form. So x as it is, derivative of log x is 1 by x, plus log x as it is, and derivative of x is 1 minus y. So this gives us 2 into 1 plus log x minus y. So since dou m upon dou y is not equal to dou n by dou x, given differential equation is non-exact. They must be equal. So we'll go for finding integrating factor. By observation you can see their subtraction, dou m upon dou y and dou n upon dou x, their subtraction is some addition or subtraction of the functions. So we have to divide it with the same type of function, that is this type, that is n. So let's see whether their combination gives us proper format. So dou m upon dou y minus dou n upon dou x divided by n. Okay, so dou m upon dou y is 2 minus dou n upon dou x is 2 plus 2 log x minus y upon n. N contains 2x log x minus xy. So let's see whether y is completely removed or not. So here we get 2 minus 2 log x plus y upon, if we take x outside, we get 2 log x minus y. So from numerator, cancellation of 2 will happen. So from numerator, if we take minus sign outside, remaining part is 2 log x minus y, which is exactly matching with denominator 2 into log x minus y. So this bracket is cancelled, remaining part is minus 1 by x. So yes, it is function of x. Y is completely removed. Therefore, integrating factor is e to the power integral of this f of x, that is minus 1 by x dx. So it is e to the power minus integral of 1 upon x is log x. This can be written as e to the power log of x inverse, that is 1 by x finally. So if we multiply given differential equation 1 with respect to by this integrating factor 1 by x, resultant differential equation is now exact.
So multiply 1 by 1 upon x. So we get here 2x log x minus xy whole upon x dy plus 2y upon x dx is equal to 0.
We'll simplify now. We'll write mdx first, that is 2y upon x dx plus 2 log x minus 1 dy. So we can see here this is of the form mdx plus ndy form. So this new function is nothing but the differential equation which is exact. Therefore, how we solve this? We integrate m with respect to x. So integration of 2y upon x dx. For x, 2y is constant and integral of 1 upon x is log of x plus c1. Now the second part is terms in n which are free from x with respect to y. So in this there is a term which is free from y is only minus 1 integral minus 1 dy, and that is minus y plus c2. So therefore solution to this differential equation is addition of this equation 1 and this equation 2. That's why 2y log x minus y is equal to c. C contains all the combinations of c1 and c2. So this way differential equation which is non-exact originally can be made exact if we multiply by its integrating factor. There are many integrating factors. We are looking at first form. One more example to fix the concept. We have this mdx plus ndy form again. So we'll write m and n. Now let's check whether it is exact or not first. So dou m upon dou y will be 4x, derivative of y is 1, plus 6y, that's it. And derivative of n with respect to x is 2x plus 2y. So since dou m upon dou y is not equal to dou n by dou x, we have given differential equation non-exact. So we go for observation of integrating factor. So their subtraction will give us the function of x and y. So if we divide it throughout by either n or m, we should get either function of x or y, not the both. Okay. So let's see what dou m upon dou y minus dou n upon dou x gives us. So this is 4x plus 6y minus 2x minus 2y. So it gives us 2x plus 4y. So x and y terms. So from n, if we take x outside, we get x plus 2y. So from numerator, if we take 2 outside, we get x plus 2y, so that can be cancelled. So yes, we divide throughout by n quantity because there is no use if we divide it by m. So divide this throughout by x into x plus 2y, that is n. So here we can write x into x plus 2y. Remaining part is only 2 upon x, a function of x purely. Therefore, integrating factor is e to the power integral of this 2 by x and dx. So e to the power 2 outside, integral of 1 upon x is a log x, and that's why it can be e to the power log of x square, and that's why simply x square. So this is x square, our integrating factor. If you multiply equation 1 by x square, we get exact differential equation. So multiply 1 by x square. So we get
4x cube y plus 3x square y square minus x cube dx plus x raised to 4 plus 2y x cube dy is equal to 0. Now this is exact.
now we will integrate m with respect to x. So we have to take new m. So it is a 4x cube y plus 3x square y square minus x cube with respect to dx. So it will be 4x raised to 4 by 4. So only x raised to 4 into y plus it will be x cube by 3. So 3 is cancelled. X cube y square minus x raised to 4 by 4 plus c1. Now the second part is nothing but integral of only those terms of n which are free from x. But there is no such term because we have just multiplied by x square throughout. So there is no such term, that's why it's in, there is no term, that's why 0. So integral is some constant, say c2. So we call this as equation 2 and equation 3. Therefore solution of such exact differential equation is x raised to 4y plus x cube y square minus x raised to 4 upon 4 plus C2 and C1. So this can be taken on second side as C, some arbitrary constant or integral constant. So this is our final answer. So today we saw how to solve non-exact differential equation. First we are converting that into exact differential equation, and before that we find integrating factor. So today we saw first rule of finding integrating factor, that is if we get that combination as functions of x, if we are able to remove y completely, then integrating factor is e to the power integral of f of x dx. Then it becomes exact, then we know how to solve exact differential equation. In next lecture, we will see second method to find out integrating factor. Thank you.